Now let's have a review first. So we already know that the assumptions or claims about the population are called hypotheses. A statistical hypothesis can be true or false, and the statistical procedure to test statistical hypothesis is called hypothesis testing. Now, one-tailed tests can be specified into left-tailed or right-tailed. So for left-tailed test, a test is left-tailed if the alternative hypothesis is expressed in the symbol less than. So illustrating the curve of a left-tailed test, we have this one, in which the tail or the rejection region is located on the left tail of the curve. For the right-tailed test, a test is right-tailed if the alternative hypothesis is expressed in the symbol greater than. So illustrating the curve for a right-tailed test, we see that the rejection region is located on the right tail of the curve. And of course, the value that separates or acts as a boundary between non-rejection region and the rejection region is called the critical value. And for the two-tailed test, a test is two-tailed if the alternative hypothesis is expressed in the inequality symbol not equal to. So since the test has two tails, so we have both the right and the left tails. So we have two rejection regions for a two-tailed test, in which the rejection regions, the boundary between the rejection regions and the non-rejection regions is determined by the critical value. Now, how to do hypothesis testing about the population mean when the variance is unknown. So we already have an idea what distribution to use if the variance is unknown. And this variance that is referred to is the population variance. Okay, so we will still follow the 6 steps of hypothesis testing. First, state the null and alternative hypothesis. Step 2, choose or identify the level of significance. Step 3, compute the test statistic. Step 4, determine the critical value. Step 5, illustrate the curve. And step 6, draw a conclusion. So when the population variance is unknown, given the sample standard deviation and n or the sample size is less than 30 and assuming the population follows a normal distribution, then we compute for the test statistic using the formula t is equal to x bar minus mu all over s divided by the square root of n, wherein x bar is the sample mean, mu is a population mean, s is the sample standard deviation, and n is the sample size, and t is the t statistic or our test statistic. Let's have an example. A store manager claims that on the average, a student spends 300 pesos weekly for milk tea. A student researcher believes that the amount is not equal than the claimed value. A random group of 25 students had an average weekly expenses of 275 pesos with a standard deviation of 90 pesos for purchasing milk tea. At 95% confidence level, can it be concluded that an average weekly expenses of a student for milk tea is not equal to 300 pesos? So let's identify what are given in this problem. So we know that the sample size is n equals 25. The claimed value for the population mean is 300. Our sample standard deviation is 90 and our sample mean is 275. And since our confidence level is 95%, then we know that our alpha is equal to 0.05. So step 1, state the null and alternative hypothesis. So we already know that our null hypothesis is that the population mean is equal to the claimed value, which is 300, And since it is stated here in the problem that can it be concluded that an average weekly expenses of a student for milk tea is not equal to 300 pesos? So meaning to say our alternative hypothesis will be written such as mu is not equal to 300 pesos. Step 2, choose or identify the level of significance. So our level of significance is already identified, which is 0.05. Step 3, compute for the test statistic. So having this formula, t is equal to x bar minus mu over s divided by the square root of n. Input our values to the variables that we have in the formula. So we have 275 minus 300 all over 90 divided by the square root of 25. And it will give us a t statistic that is approximately equal to negative 1.39. So the test statistic is negative 1.39. So step 4, let's determine the critical value. So in determining the critical value, we need to determine first the degrees of freedom. So df is equal to n minus 1, in which n is the sample size, and our sample size is 25. So df is equal to 25 minus 1, that's equal to 24. And using our t-table, and since our test is a two-tailed test, let's look for the critical value at alpha equals 0.05 in the areas in two tails with the degrees of freedom of 24. So this is the table, the table of t critical values. Again, our test is two-tailed. So we will use the area in two tails, and our alpha is 0.05, so we'll use this column. And since our df is 24, so getting the intersection of df equals 24 and alpha equals 0.05, we have 2.064. So the intersection is 2.064. And since our test is a two-tailed test, then we have two values for the critical values. So we will get positive 2.064 and negative 2.064. So now we can illustrate the curve. Again, in illustrating the curve, we have to identify first where our critical values are located. So here is our curve, and our critical values is at negative 2.064 and positive 2.064. So locating, it's approximately here, wherein the shaded regions are our rejection region. So now that we have already identified our rejection region, let's now locate where our test statistic is. So since our test statistic is equal to negative 1.39, then our test statistic is approximately located here. And we see that our test statistic is located on the non-rejection region. So in conclusion, we say that there is no sufficient evidence to indicate that the average expenses of a student in purchasing milk tea is not equal to 300 pesos. Because as I said, if the test statistic falls in the non-rejection region, meaning to say we fail to reject the null hypothesis. So there is no sufficient evidence to claim that our alternative hypothesis is true. Now let's have example 2. A manager claims the average time a middle-aged adult spends on watching K-drama is 500 minutes. So a student researcher believes that this had decreased. He gathered data from 20 adults and it resulted to a mean of 490 minutes with a standard deviation of 90. At 99% confidence level, can it be concluded that the average time a middle-aged adult spends on watching K-drama is less than 500 minutes daily? So let's identify our given So we know that our N here is 20, our sample size is 20, our population, our claimed population mean is 500, our standard deviation, sample standard deviation is 90, and our X bar, or the sample mean, is 490. So since the confidence level is 99%, then alpha is equal to 0.01. So step 1, state the null and alternative hypothesis. So take note that our null hypothesis is that the mean is equal to the claimed value, which is 500. And since we are asked about, can it be concluded that the average time a middle-aged adult spends on watching K-drama is less than 500 minutes? So we have less than here. So our alternative hypothesis should be expressed as the population mean is less than 500. Step 2, identify the level of significance, in which we have already did. So that's alpha is equal to 0.01. Step 3, compute the test statistic. So computing for the test statistic, we'll use the formula T is equal to X bar minus mu all over S divided by the square root of N. So plug in our values to the formula. We have 490 minus 500 divided by all over 90 divided by the square root of 20 is approximately equal to negative 0.50. So our computed test statistic is negative 0.50. Next, step 4, determine the critical value. So in determining the critical value, we need to identify first our degrees of freedom. So df is equal to n minus 1. So our n here is 20. So 20 minus 1, that's 19. So our degrees of freedom is 19. Next, we know that our alternative hypothesis here is expressed in the less than symbol. So our test is a one-tailed test. And since this is a one-tailed test, then we will be looking for the intersection of our degrees of freedom and alpha equals 0.01 at area in one tail. Okay, so to show, let's have our t-table here. And since our test is a one-tailed test, so we will use the area in one tail. And our alpha is 0.01, so we will use this column. And since our df is equal to 19, so getting the intersection of 19 and alpha equals 0.01, we have 2.539. So that's our, critical value. Now, since our test is a one-tailed test, specifically a left-tailed test, because our alternative hypothesis is expressed in the less than symbol, then we only have one value for the critical value. And since it's a left-tailed test, then we'll use negative 2.539 as the critical value. Next step, illustrate the curve. So in illustrating the curve, let's locate first our critical value. And since our critical value is negative 2.539, so approximately locating our critical value, so that's negative 2.539 is somehow located here. And the shaded region is our rejection region. And going back to our step 3, our computed test statistic is negative 0.50. So locating negative 0.50, it's somewhere here. So we see that our test statistic falls in the non-rejection region. So as a conclusion, we say that there is no sufficient evidence to indicate that the average time spent of an adult in watching K-drama is less than 500 minutes. Okay, we failed to reject our null hypothesis. That's why there is no sufficient evidence to indicate or to claim that our alternative hypothesis is true. Next, let's have example 3. It was announced over the radio that the average price of a kilogram of pork in Metro Manila is 195 pesos. However, a sample of 15 prices randomly selected from different markets in Metro Manila showed an average of 200 pesos and a standard deviation of 9.5 pesos. Using 0.05 level of significance, is there a sufficient evidence to conclude that the average price of pork is more than 195 pesos? Assume that the population is normal. So let's identify what are given. So our N, number of samples, is 15. Our population mean is 195. Our sample standard deviation is 9.5. Our sample mean is 200. And our alpha is 0.05. Step 1, state the null and alternative hypothesis. So our null hypothesis is that the population mean is equal to 195. And since we are asked if there is a sufficient evidence to conclude that the average price of pork is more than 195, so our alternative hypothesis is expressed as the population mean is greater than 195. Step 2, identify alpha. So our alpha here is 0.05. Step 3, compute for the test statistic. Computing for the test statistic, we have 200 minus 195 divided by, or all over 9.5 divided by the square root of 15 is approximately equal to 2.04. Next, determine the critical value. So still in determining the critical value, we need to find the DF first. So our degrees of freedom is equal to n minus 1, and our n here is 15. So 15 minus 1 is 14. And since our test is a one-tailed test, because our alternative hypothesis is expressed in the greater than symbol, so using the t-table, locate or find the intersection between df equals 14 and alpha at 0.05 using the areas in one tail. So to show, we have here our table of t critical values. Again, our test is a one-tailed test, so we will use the area in one tail. And our alpha is 0.05, so we will use this column. And since our DF is 14, finding the intersection, we have 1.761. So 1.761 will be our basis for the critical value. And since we know that our test is a one-tailed test, specifically a right-tailed test, so our critical value is the positive 1.761. Okay, so illustrating the curve, let's locate first our critical value, which is positive 1.761. So it's somehow located here. So that's where our critical value is, and the shaded portion is the rejection region. Now, let's go back to our step 3, and our computed test statistic is 2.04. So locating 2.04 in the curve, it's here, way past or just slightly passing through positive 2. And we see that our test statistic is located or falls within the rejection region, within the shaded region. So in conclusion, we say that there is sufficient evidence to indicate that the average price of pork in Metro Manila is more than 195 pesos. Next example. A sport trainer wants to know whether the true average time of his athletes who run a 100-meter sprint is 98 seconds. He recorded 18 trials of his team and found an average time of 98.2 seconds with a standard deviation of 0.4 second. is there a sufficient evidence to conclude that the mean time of the team is not equal to 98 seconds at 0.05 level of significance? So first step, before we go to step 1, let's identify what's given first. So our N here is 18 because he recorded 18 trials, so N is 18. Our population mean is 98. Our sample standard deviation is 0.4, and our sample mean is 98.2 with a level of significance of 0.05. So step 1, state the null and alternative hypothesis. So our null hypothesis will be the population mean is equal to 98, and our alternative hypothesis will be the population mean is not equal to 98. Step 2, we know that our alpha is equal to 0.05. Step 3, computing for the test statistic. So plugging in our values to the formula, we have 98.2 minus 98 all over 0.4 divided by the square root of 18. It will give us approximately equal to 2.12. So our computed test statistic is 2.12. Step 4, determine the critical value. So first, we have to identify our degrees of freedom. So that's n minus 1. So n here is 18. So we have 18 minus 1, that is 17. And since our test here is a two-tailed test, because our alternative hypothesis is expressed in the not equal to symbol, using the t-table, we'll look for the intersection of degrees of freedom, that is 17, and alpha equals 0.05 at area in two tails. To show, we have our t-table here. Since our test is a two-tailed test, so we will use area in two tails, and our alpha is 0.05, so we'll use this column. And since our df is 17, so our intersection is at 2.110. So this intersection will be the basis for our critical value. So since our test is a two-tailed test, so we know that we have two values for the critical value. So we have positive 2.110 and negative 2.110. Step 5, illustrating the curve. Identify first where are your critical values are located. So we have here negative 2.11 is somehow here, and positive 2.11 is somehow here also. Shading to the left of negative 2.11 and to the right of 2.11 are our rejection regions. So next, we are now done identifying our rejection region. So next step will be locate our test statistic. So our computed test statistic is 2.12, positive 2.12. So our critical value is 2.11, positive 2.11 on the right tail. So our test statistic is very close to our critical value, wherein our computed test statistic is 2.12. So meaning to say our test statistic falls on the rejection region. Since our computed test statistic falls on the rejection region, so in conclusion we say that there is sufficient evidence to conclude that the average time for the team in a 100-meter sprint is not equal to 98 seconds. Okay, so basically just the same process when we do hypothesis testing for the population mean when the variance is known. It's such that the difference is that how you'll find the critical values. So when the variance is known, you will use the z-table. But when the population variance is unknown, given the sample variance or the sample standard deviation, then we will use the t-distribution. Alright? So that's all. It has been a wonderful and worthwhile journey with you all, grade 11 STEM students. See you maybe in due time, and thank you.